In the next slide, we want to study what is the matrix W bar. So let's recap. W bar is an n by n matrix, C is a n by 1 column, and X is a n by 1 column. What are the elements of W bar? Well, let's now write it as X is equals to W bar times C. So we have X here, the first element, second element, until the n-1 element, these column vectors of X. Now we have expanded W bar and C into this form. So C0 times the first column of W, C1 times the second column of W bar, C2 multiplied by the third column of W bar, and so on. So we now see that the W bar is equals to 1, 1, 1, then followed by 1, E plus J, 2 pi over n, second one is E plus J, 2 times 2 pi over n, and so on. The third one is 1, E plus J, 4 pi over n, E plus J, 2 times 4 pi over n, and so on. This, all the 1 is this, the first column. The second column is here, and the third column is here. Where are the C's? Well, what you do is that you have W bar multiplied by C, so you have C0, C1, C2 here until Cn-1. In the matrix times vector notation, you realize that you can interpret it as C0 times the first column, C1 times the second column, C2 times the third column, and so on. And therefore now we are writing it, the matrix vector multiplication, in this relationship. C0 multiplied by first column, C1, second column, and so on. The last column, of course, is the last element of C, which is Cn-1, multiplying by the last column of W bar. Where did I get all these elements from? Well, you realize that I got it from this expression over here. It is nothing but expanding for different k's and different n. So B0 is for k equals to 0. B1 is implying for k equals to 1. Then what about these elements coming down? This is element n equals to 0, n equals to 1, n equals to 2, and until n equals to n-1. So these elements here is changing little n. Different columns are changing different k's. So you now know how we have constructed the W bar matrix. Now it is important to understand how to visualize each of these columns. This is a real column vector, all ones. It doesn't change. You can have a say that it has a DC frequency, direct current frequency. It is a non-changing value. This guy looks very familiar. Starts with 1, and in fact all the amplitude is 1. The only thing that is changing is the phase. And you realize that from this point to this point, the phase changes by 2 pi over n. From this point to this point, it also changes by 2 pi over n. You see, it's 2 pi over n. The next guy is 4 pi over n. It changes only by 2 pi over n. Then in fact, the next point also 2 pi over n. If you compute this carefully, this is a phasor that will be rotating anti-clockwise, and it will take n samples to reach the next one again. Let's visualize this. I'm going to sketch for you the all ones here. Why do I say that this is all one? How do I interpret this little circle here? This circle is the unit circle, and this is the real axis, and this is the imaginary axis, and this value is 1 and the second value is 2. This is the origin over here, and this is -1 and -2. On top is j, and then the bottom is -j. So if I want to denote a vector that has value 1, I put it here. So this is the vector, and it reaches 1, touches the circle. So the horizontal axis is the real line. I want to say that I have a column vector of all 1. So I'll use this circle and this phasor to represent it as all ones. There are 8 of them to show this 8 value in this example. How about this guy? The first element is 1, the second element is ei 2 pi over n. In our example later on, you'll realize that capital N is 8. So 2 pi over 8. We basically divide the circle into 8 parts. Each time we move from here to here, it is 2 pi over 8. The second time we move is another 2 pi over 8. So 1, 2, 3, 4, 5, 6, 7, 8. It takes 8 samples to reach back to the same point. Now, we're going to see that it reaches here after 1 sample, reaches here after 2 sample, here after 3rd sample. So let us see, in the first n equals to 0 is along the real line. It moves by 45 degrees after 1 sample, move by another 45 degrees after the next sample, and so on. So after 8 samples, it will, or in the 7th sample, you'll reach the last point, and in the 8th sample, I should say x of 0 or x of 8, you'll reach back to the same point. So you'll see that actually the column vectors are complex phasors of different frequency. B0 is a column vector of the same frequency, or no frequency, not changing at all. B1 is a phasor that rotates anti-clockwise and takes n samples to reach 1 complete cycle. B2, you will realize that it is moving faster than B1, twice as fast. From here, it was the same, but here it actually moves twice as fast. It takes 1 sample, it already moved 90 degrees. Another sample, it takes 90 degrees. Because it moves twice as fast, it will complete 2 complete cycles in n sample. B3 is moving even faster. See, from here it moves 3 times faster than the first column. So this is 135 degrees, another 135 degrees, and so on. So in n sample, you move by 3 rounds. It's very nice. So once you can visualize this square matrix, you realize that the elements of this W bar are nothing but rotating phasors of unit length at different frequencies. Okay. With that, you can fill up the elements of W bar. Lastly, I show you another visualization. Let's visualize again B1 again. B1, remember, it is a column vector of n elements. It is a complex phasor rotating anti-clockwise. Let us see in 3D now. So remember that along here is the real line. The first element, this value is 1, and the horizontal axis is the real line 1, and the vertical axis is the imaginary axis. After 1 sample, it is rotating anti-clockwise, and how do we know? Well, this is pi by 4. one sample, it moves by pi by 4. See, 2 pi divided by 8. Let's write down 2 pi divided by 8. K equals to 1, n equals to 1. So we have pi by 4. Right. So anyway, as we are moving n, it starts to rotate. And what is this axis here? This axis is time, and time is coming out into here, different time. The phaser is rotating anti-clockwise, and after 8 sample, it will come back to 1 again. What about B2? Same, it's the same, rotating phaser of unit length, rotating faster, and B3 is a phaser rotating even faster. So this is how we interpret the columns of W bar, and we can call the columns B0, B1 until B7, and the index K here. Now remember, it is denoting the harmonics, how fast is it rotating. I'll leave the explanation, the detailed explanation here. You can read all about it. So in the last few slides, we have been interpreting W bar. Thank you.